Hello everyone, today we will talk about reacting mixtures and combustion. My name is AZRI Azhar bin Muhammad Azra and my matrix number is 23002072. What again? My name is AZRI 23002072. So we will discuss about reacting mixtures and combustion. For first thing is we need to understand the combustion, air fuel ratio, heating value, flame temperature and exergy. So I will explain the fundamentals of reacting mixtures and combustions. We will cover combustion reaction, theoretical air, heating values, adiabatic flame temperature, and finally exergy analysis. So what is combustion? Combustion is a chemical reaction between fuel and oxygen that releases energy. Complete combustion occurs when all carbon becomes carbon dioxide and all hydrogen becomes water. For example, methane burns according to the reaction shown. As we know, CO2 is carbon dioxide. And hydrogen will become H2O. What is it? It is a water. And then sulfur becomes sulfur dioxide. Sulfur dioxide. So we can show that the methane burns according to the reaction shown. So methane plus oxygen, double the oxygen, we will have carbon dioxide and water. So first step, we have CH4 plus O2 will equal to CO2 and H2O, and then we will similarize both of the left and right equation. So we see that the carbon is enough, so the oxygen will be enough too, so it is already complete, and this is also very complete. So we will need to change the oxygen and H2O the numbers of it. So to include H4, if we have 4 hydrogen, so the H here will have to have many also. So in order to have 4H on the right side, so we will add 2 H2O, CO2. So the right side is complete, and then we will count the oxygen on the right side. 1, 2 and 3, 4. So we have 4. So we need to change the oxygen numbers to 2O2 plus CH4, and we will get the simulation. So next, combustion air and air fuel ratio. Since pure oxygen is rarely used, combustion usually uses air. Air contains approximately 21% oxygen and 79% nitrogen. The air fuel ratio tells us how much air is applied for combustion. So we have 21% oxygen and 79% nitrogen. Every mole of oxygen is accompanied by 3.76 moles of nitrogen. 3.76 moles of nitrogen. Air fuel ratio measures air supplied relative to fuel. So air is very needed in a combustion. Higher, so measures amount of air supplied relative to fuel. Higher, if the AFR is high, so it will means more air. But if the AFR is low, it will means less air. So the air composition pie chart is needed. But so we will make pie chart 79%. This is 79% of nitrogen, and this is 21% of oxygen. So this is how it will be in the pie chart. We will have many more like carbon dioxide, but this is the ratio in the combustion. And then we will move to theoretical air and excess air. Theoretical air is the minimum amount needed for complete combustion. In practice, extra air is usually supplied to ensure all fuel burns completely. However, excessive air can be reduced combustion and temperature. So, theoretical air is equals to minimum air required for complete combustion, and excess air ensures complete combustion. Too much excess air lowers flame temperature. But why we use excess air? We use excess air to ensure complete combustion and reduce unburnt fuel. Excess air ensures complete combustion and also reduces unburnt fuel. So what is excess air means actually? So for example, it is 150% theoretical air, 150% theoretical air is equal to 50% excess air. So we will only need the 100% theoretical air, so we don't have any of it. So if we have 167% of theoretical air, so we will have 67% of excess air. And then we will move on to enthalpy of formation. To analyze reacting systems, we use enthalpy of formation. Stable elements such as oxygen and hydrogen have zero reference values, while compounds have positive or negative formation enthalpies. Energy released or absorbed when compounds form from elements. So the reference state is 35 degree at 1 atmospheric pressure. So we have what the importance of it? The importance of it is we use it in energy calculation for combustion system. Moving on is the heating value of fuel. Heating value measures how much energy a fuel can provide. HHV assumes water condenses and releases additional energy, while LHV assumes water remains as vapor. So we will need to remember HHV is water leaves as liquid, and LHV is water leaves as vapor. H for liquid and L for vapor. What does it mean? Higher heating value. higher heating value, so the water leaves as liquid. If lower heating value, the water leaves as vapor. At HHV, more energy is recovered. At lower, less energy recovered. More energy recovered. LHV, less energy recovered. So for example, we have obtained that its LHV is approximately 44,430 kilojoule per kilogram. Moving on, adiabatic flame temperature. What is the definition of it? Maximum temperature during combustion with no heat loss. The adiabatic flame temperature is the highest temperature achievable during combustion when no heat escapes. The maximum value occurs at theoretical air because excess air cools the combustion products. So highest at theoretical air, and it is excess air dilutes products and lowers temperature. So the key idea is the more excess air, so the more dilution, so the lower flame temperature. If the maximum temperature it is occurs at theoretical air condition. Means that it is maximum temperature during combustion without losing any heat. So next one is AZRI concept. What is AZRI? It is maximum useful work obtainable. So the energy is conserved. If the energy is conserved, energy is always conserved, but AZRI measures how useful that energy is. So we calculate how useful the energy is when the energy is conserved. Fuel has high AZRI because it can produce work, while combustion products have much less useful potential. Combustion products less useful potential. So what is the meaning of it? Energy and AZRI. Energy is a form of work, but AZRI is maximum useful work obtainable from a system. Moving on is the exergetic efficiency and its conclusion. In conclusion, a combustion is the foundation of many energy systems. Understanding air-fuel ratios, heating values, flame temperature, and exergy helps engineers design more efficient and sustainable thermal systems. So it measures conversion of fuel exergy into useful work. For example, 40% exergetic efficiency. So it means that 40% useful work. Combustion releases energy. Air-fuel ratio affects performance. Heating values quantify fuel energy. Flame temperature depends on air supply. Exergy measures energy quality. So this topic is very useful for the engineers out there to make their products more efficient in terms of combustion. That's all from me. Thank you.